it's helpful to kind of look back on it later. So I'll probably just post it to my YouTube in case somebody wants to watch it again. So again, you can be writing this down or you can taking a screenshot of this. We will go over this many times, but this is really important that you understand the order of this. So for related rates, these are generally word problems. And so in that word problem, you should always start by reading the question. I don't know why I didn't include that, but the first thing you should always do is read the question. That kind of goes without saying, except math guys, they like to skim for information. Make sure you're actually reading the scenario. Sometimes there's important information that's not easily found just by skimming. You want to determine what's given, and actually you want to determine what they're asking you to find as well. So that's like the first step, is to kind of determine what information you're given and write it down in terms of variables. That way we can just look at our chart of information instead of going back to the paragraph every time. And you want to determine what you're still trying to find out. Okay, step 2 is write an equation that relates those variables. Okay, and we'll talk about how to identify that equation. Sometimes it's given. A lot of times you have to determine what equation makes the most sense. And there's a little star next to question number 2. If you're given any constants right away, so anything that's not changing in the equation, that's a value, you want to plug those constants in immediately. Okay, if you wait to plug them in, it makes the derivatives harder. And step 3 is take derivatives. So we're going to find our givens, write them as variables, write an equation relating those variables, plug in any values that are not changing, and then we're going to differentiate, which means take a derivative. Okay, then after we take the derivative, that's when we're going to substitute all the other information in. So we're only substituting information in that is a constant at the beginning. Anything else that's changing gets plugged in after we take a derivative. And then we're solving, and a lot of times these problems have units as a part of them. Not always, but a lot of times they have units. So you want to make sure your units make sense as a final answer. Okay, hopefully everybody had a chance to write this down. We'll come back to the screen another time. And again, I'm recording this in case you want to review it. So let's talk about this first one. Please don't take time to write all of these down. That's why I'm recording this. And I stole these from your Princeton Review. So I actually, like, word for word took them from your Princeton Review. So in case you want to go back and review them, they're there also, most of them that I stole. So first thing we're going to do is read the question. It says a circular pool of water is expanding at the rate of 16 pi inches squared per second. At what rate is the radius expanding when the radius is 4 inches? That's a very common related rates question. So I have some scenario, it's in kind of a paragraph, it's more of a word problem, and it's asking me about rates given other rates. So what's happening is I have this circular pond of water. I'll go this way, but really it's like a circular pond of water right on the floor. And it's expanding. And it says it's expanding at a rate of 16 pi inches squared per second. The units sometimes give you a hint as to what that thing is. So an inches squared, right? A distance squared is what kind of information? Unpause yourself if you think you know. An inches squared. What kind of information would an inches squared by itself be?
Area.
Area, perfect. So we have a change in our area divided by seconds. So that means I have a change in area with respect to time. So what that first piece of information is, and the first thing we're going to write down is dA over dt is equal to. So that means a change in area with respect to time or over time. And your unit should make sense, right? So area is like inches squared. Time is like seconds. So a change in area over a change in time, and that's given by 16 pi. Now I'm going to leave the units off just for our information here because we don't need to plug units into our equation, but we'll remember to come back to those units later. Okay. Then the next thing says, at what rate is the radius expanding? So we're looking for a rate of change of radius. That means what we're looking for is a dr, change in radius with respect to time. I'm just going to put a question mark there. That's the information we don't know. Okay, so we're looking for a dr dt. That's a change in radius with respect to time. Okay, because it wants at what rate the radius is changing. And then it gives us the information that when the radius is 4 inches. So when r equals 4. Okay, and I'm not writing radius equals. I'm making up reasonable variables for these things. So area, I'm calling area A. A change in area with respect to time, that's a dA dt. Radius, I'm calling R. A change in radius with respect to time, that would be a dr dt. This is a really important skill in order to do those related rates. This is a lot of what your homework's on tonight, is just identifying the variables, kind of writing down what's given in the problem. Okay, now what we need to do is we need to come up with an equation that relates these variables in this scenario. So I have a circular pool of water and it's expanding, right? And it's a circle. So it's a circle expanding, and with respect to that circle, we're talking about things like area, and we're talking about things like radius. So what is an equation that you might write that relates that information, our scenario of a circle, an area, and a radius? Anybody unmute yourself? Go ahead. Anyone?
Can I take a guess?
Yeah, go for it, Noah.
Or should I do it in relation to like the variable?
No, just general equation. So not using any of the variable stuff, just
Okay.
general equation.
16 pi equals 4 question mark.
Okay, so not quite. I will work this one out for you. So we have a circle, right? We're talking about area and radius. Can anyone come up with an equation that relates circles, area, that maybe has a radius in it? Someone left a comment, but I'm not looking at the comments right now. So just unmute yourself if you have an idea.
Area equals pi r squared.
You got it, 100%. That's the equation. Area equals pi r squared. Some of you are like, oh, duh, I thought it was like way more complicated than that. No, that's the idea, but it doesn't give you that equation, right? It doesn't tell you to use that equation. It tells you, here's the situation. We have a circle. Then it doesn't even, the word area is not even in here, right? You have to determine its area based on the fact that it's in inches squared, right? And then it tells us a radius. So yeah, that's our equation. That's the thing we're starting with. Now, the next thing we do is we plug in any constants. Now, constants mean things that are not changing. So again, it told us that it's expanding at a rate. Well, I don't have a drdt at all in this equation, so I cannot plug a drdt into this equation. I don't have one, so I cannot plug in that first piece of information. Some guys think that it says, well, r is 4, so we can plug 4 in right away. But r is not constant. If you think about the situation, right, the circle is expanding. So there's a moment in time when r is 4, but it's just a moment. It's changing, right? So that r is not constant either. We're saying there's a moment when r is 4, and at that moment, I want to know what the rate of change of the radius is. But that moment is just a fleeting moment. It's not always r equals 4. So we don't have any constants to plug in. So now what we need to do is we need to take the derivative. This is where implicit differentiation comes in. You'll notice on the left side where we have our constants, we have stuff with respect to time, dt, which means I need to take the derivative of both sides. This is implicit differentiation with respect to time. I need to take the derivative with respect to time. So the derivative of a with respect to time, if I took that derivative, is dA over dt, right? It's like a to the first, so it's 1a to the 0, which is just 1, and then times our dA dt, which is our chain rule. Okay, now our pi is a constant. So if I give you like 3x squared or something like that, you would take the 2 and multiply it by the 3, right? You do 2 times 3, x to the first power, and then times whatever the derivative of x is. Now we don't have an x in this one. We're working with an r. Our derivative of pi r squared, any guesses? Anyone want to unmute and take a guess of the derivative of pi r squared with respect to time? Come on, come on.
2 pi times r dr over dt.
So say that again, Nico. I missed the very first part.
2 pi times r times dr over dt.
You got it 100% correct. Fantastic job, right? So he took the 2, multiplied it by the pi. Then we still have the r, and the r gets raised to like the first power. And then we multiply by the derivative of the r, right? Again, that's chain rule. So we're multiplying by the derivative of the r with respect to time. So that gives us a dr dt. Okay, now we have a lot of information. Now that we've taken the derivative, now we can start substituting things in. So I have my 16 pi, that's going to go over here for dA dt. You can plug it right in. You don't need to come up with the decimal equivalent. It's not going to be helpful. You can even see in the equation, those pi's are going to cancel out. Okay, we still have a 2 pi on the right. We can plug in our r. Now that we've taken the derivative, we can plug in our r of 4. And the thing we're looking for is dr dt, so we'll just leave that here. Now, one thing you can do is you can isolate that dr dt first if you want, but it's fine either way. Like if you want to get all the 2 pi r to the other side first and then plug stuff in, go for it. But it's fine either way. It doesn't buy anything. Okay, now because I'm solving for the dr dt, I'm going to divide both sides by 2 pi times 4. Let's just simplify that. We're going to divide that by 8 pi, right? That's what 2 pi times 4 is, divided by 8 pi. And so I get an answer of 16 pi divided by 8 pi, which is just 2. So we get 2 is equal to our dr dt. Okay, that's the rate of change, but that information does not have units on it. My units need to make sense. So I need the units that would express a change in radius over a change in time. So remember, when it was a change in area, we had inches squared. We had an area information divided by seconds, a time information. What do you think the units will be for dr dt? Someone else who hasn't unmuted yet.
Inches per second.
Inches per second, you got it. Perfect. That's the exact answer. That's the whole thing. Are there any questions? Just unmute yourself if you have a question, because I can't see everyone. I'm trying to expand my screen so I can see more people. Okay, we are going to start the next one. We only have a couple minutes left, so we're not going to get very far. Question 2 says, a 25-foot ladder is leaning against a wall and sliding toward the floor. If the foot of the ladder is sliding away from the base of the wall at 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? Blah. This is a super common question. They call it literally the ladder problem. So if you get stuck or you want extra help, literally type into YouTube ladder problem, and you're going to see a billion examples of this one. They put it on so many exams. Okay, the situation I have a wall. There's my wall. And I have a ladder. Here's my ladder. The ladder is sliding. I'm trying to find something that's colorful. The ladder is sliding down the wall, right? Like how that would work, gravity. We're pretending everything is frictionless. We're in a perfect world. All you physics guys are like, what? What's the coefficient? No, it's just frictionless. Don't worry about it. It's sliding perfectly down the wall, okay? A lot of you guys would think, well, isn't whatever rate it's sliding this way going to be the same as the rate it's sliding this way? And no, that's actually not how that works. Those rates are dependent on the equation that relates that information. So I like to label this as X. I like to label this as Y. I'm going to do this basically every time we have a triangle. And I like to label this as R. Some people call it Z. I like to call it R because it relates to more information in the future. Okay, so we have some information. We have an information about the rate it's moving. So I'm just on my picture going to call that dx dt because that's the rate of change of the base. So the base is getting longer. There's a moment where the base is a certain length, but it's moving at a rate, which would be our change in x over time. Then we have this one sliding down the wall. That would be a dy dt. Now, this is not a magic ladder. This is not a beautifully expanding and shrinking ladder. This ladder is not changing, right? This ladder is constant. No matter what with the sliding, the ladder itself stays at 25 feet. So that's the first thing we could write down is R equals 25. And if I took the derivative of that, if I wanted to know the rate of change of the ladder, it would be 0. But we're not going to need that rate of change because we are going to plug it in immediately. We are out of time. That took a lot longer just to even start that problem. I know is a lot of reading. That's all I have for you today. There is some Khan Academy. It's mostly just identifying variables and stuff like that to start, and then we'll pick this up next time. I will see you guys later. Have a great day. I'll stay on if anybody has questions.
Thank you.
Thanks, y'all. Charlie, are you alive?
I am. My computer like still is not connected to the internet at Brophy.
Okay, go
So-
talk to tech. Go take it down to tech ASAP, because obviously with classes, you're going to need your computer to work.
Yeah.
I saw when you submitted your last answer, so you worked for a good amount of time, and we'll figure that out. I'll adjust things as needed, because I know that you got dropped and that's what happened.
Yeah.
I don't know why no one else got dropped. That's the weird thing. Maybe it's because you're outside, or maybe it's a specific
Yeah.
area on campus. But go
Yeah.
take your computer to tech and go figure that out. And then if you could just follow up with an email to me and to tech, like copy both of us so that I can see what kind of those conversations were.
Okay.
Cool.
Thank
Awesome. Thanks, Charlie.
Bye.
Bye.